You all talk briefly about finding eigenvalues and eigenvectors. So let's just say we start out with this matrix A equals 3, 0, 0, negative 4. And we know that an eigenvalue is a value lambda, and its corresponding eigenvector is a vector v. A is 2 by 2, v is 2 by 1, and lambda is a 1 by 1 scalar. So an eigenvector and eigenvalue pair is any pair of lambda and v that satisfy this equation, which is equivalent to saying AV minus lambda V equals 0, which is equivalent to saying A minus lambda I times V equals 0. The I is there because you can't subtract a scalar from a 2 by 2, and the identity matrix I, which contains 1, 0, 0, 1, looks like the 2 by 2 identity is consistent of values 1, 0, 0, 1. Okay, so that's equivalent to the identity multiplier 1 in scalar form. And so after we have that, we want to find lambda. We're solving for lambda first so that v is non-trivial. That means we don't want the 0, 0 solution. And this is accomplished from some linear algebra theory by finding lambda so that the determinant of a minus lambda I is 0. So we're going to calculate a minus lambda I, find its determinant, and set it equal to 0, and solve for lambda to satisfy that equation. So we proceed. We have a minus lambda times I. We distribute the lambda into the matrix. So negative lambda times 1, lambda times 0, lambda times 0, lambda times 1, and then subtract it away. So we get 3 minus lambda because of the lambda that appears here. We get 0 here since we're doing 0 minus 0, 0 minus 0, and lambda times 1. So we have negative 4 minus lambda there. Okay, well, next we proceed to find the determinant of that. So the determinant is the product of the diagonals from left to right minus the diagonals from bottom left to top right. And we get this quantity here. Now we want to set that equal to 0. And so if we set this equal to 0, because this is already in factored form and this zeroes out, we just get lambda 1 equals 3, lambda 2 equals negative 4. So from an A matrix that has a 0 along either above or below the top left to bottom right diagonal, you can pretty much read off those eigenvalues straight from the matrix. So now step 2, for each eigenvalue, we need to find an eigenvector. Each eigenvalue has its eigenvector, and so we need to plug each eigenvalue back into this equation, a minus lambda I v equals 0. We could plug it into the original equation back here, but this is the more optimal form to calculate v from, since v is already we've factored out a v and we have only one v left. So what we're going to do is we'll calculate, first of all, a minus 3i for the first eigenvalue, and we get 0, 0, 0, negative 7. So that seems kind of suspicious. Well, that's actually a good sign. We want one of the rows to zero out. What we've done is we've essentially created two linearly dependent equations. And we're not going to talk about that here. But anyway, so now we need to solve a minus 3i times v equals 0. So that means this, which is this is a minus 3i, v, which contains our two variables, x and y, and that's going to be our eigenvector, equals 0, 0. So we write that in scalar form. The first row reads 0x plus 0y equals 0, and the second row reads 0x minus 7y equals 0. Now, the first row is kind of useless, so we hope to have one row that's useless, because what we are aiming for is to have infinitely many possible solutions. One equation should always zero out. The second one reads that 0 times some number minus 7 times another number must equal 0. Now, the reason I'm putting this out there in words, I know you can read it and you can understand it, but the emphasis here is that you might say, well, the only values that work are 0 and 0. However, you'd be right in saying that y must equal 0, because the only non-zero contribution to the left-hand side is this term here. And so if y is 0, x can be anything we want it to be, because 0 times any number is 0. So for example, the value x equals 1 and y equals 0 will work in that equation. The value x equals 2, y equals 0 will satisfy that equation. Definitely satisfy the first one, because 0 times any number is 0, and 0 times any other number is 0, and add them together, you still get 0. And so other than 0, x can be any number, and y must be 0. Y is 1, for example, then you'd have negative 7 on the left, but 0 on the right, and that would not be an equality. Now, for simplicity, you can pick anything you want. Every computer will kind of pick different eigenvectors, But one simple one, or we call the basis vector, is 1, 0. It's easy to work with ones and zeros. And so we would choose v1 equals 1, 0. You could have also picked 2, 0, or even pi 0 if you wanted to. The point is that any eigenvector that you pick must be a scalar multiple of every other eigenvector that's feasible. So x could be any number, but y must be 0. Okay, so that's our eigenvector. Now we're going to implement this in Octave Online, octave-online.net, or you could use MATLAB just the same, assuming you have the symbolic package installed. So the first thing we're going to do is define the matrix A, and the way we do that is we define the matrix A equals, and then we have to use square brackets. The row elements are separated by commas, so the first row is 3, 0. The semicolon in here actually says go to a new row, and then in the new row 0, -4, enter those values, and we'll run these line by line. So we're going to define matrix A, and I'm going to just paste it in here just so that you can see the output without it being suppressed by the semicolon. And you don't have to have the semicolon there, just will of course suppress the output if you run the script. So the next thing we want to do is we want to find the eigenvalues by solving for lambda so that determinant of A minus lambda I equals 0. Note, a 2x2 identity matrix can be found in Octave MATLAB by typing EYE parenthesis 2. So that just says create the identity matrix 2x2. The reason it's used I like eyeball is just because I think we don't want to use the capital letter I. It's just easier to call it something else. So anyway, I2 will produce 2x2. I3 will produce what we call the 3x3 identity matrix, and so on and so forth. Just a simple little feature that makes it quick to run these things. The first thing we're going to do is we're going to, because the output is going to be a pairing of solutions, we're expecting 2 solutions for a 2x2. So the output is going to be in the form of a vector. Okay, so what I'm going to do is I'm going to assign to some quantity that I'm going to call eval. So just so that I can grab the outputs. I want the determinant of A minus L times I2. Okay, so make sure we close our parentheses, a little bit easier to space things out. Now, because I'm treating L as a symbol, before I run that, I would need sims L to define the symbolic value L. So I'm going to type sims L, that's going to initiate a symbolic variable there, and now in this case, I want this set equal to 0. So I'm going to set that equal 0, since it's a logical expression. And I want to solve that equation. So I've got to tell MATLAB or Octave that I want to solve it. And then I want to solve that for comma L, close parenthesis. And so I'm going to suppress that output because I'm not going to want to see that when I run the script. But I will go ahead and execute it here. So there we go, executing that, and it produces the output in this vector called eval. So one of the eigenvalues is -4, one of the values is +3. Now it doesn't matter which one you call lambda 1, lambda 2, it's really arbitrary. It's just important to keep them as their associated eigenvector. So I'm going to create these new symbols L1, and that's going to be lambda 1. And what I want is whatever is the first element in my eval vector. Okay, so in this case it's going to be -4. I'm going to call it lambda 1. Okay, so I'm going to run this so you can see that it's just going to grab -4, the first element from the eval vector. And now I want to do the same thing, but I'm going to copy and paste this. I'm just going to change the 1s to 2s, and now it's going to grab the second element. Okay, so copy that, suppress it in the script, but show it in the window here just for illustrative purposes. Great, we've got that. Now we want to solve for v in the equation A minus lambda I v equals 0. Okay, so the way we're going to do this is it's sort of twofold. 2 ways you can go about doing this, or a number of ways actually. But we want to solve A minus lambda I times. It doesn't really matter whether we use AV equals lambda v, or but this was like 3 steps down where we isolated. We're able to factor out v. It just makes more sense to use this form of the equation AV equals lambda v, so you don't have to do all the work over again. And so what I'm going to do is I'm going to do A minus L1 times I2. It'll give me the resulting matrix for, and I'll come back to this in a second. So if I do this, that takes away, and if I do this with L2, we're going to see that matrix that we actually got, 0, 0, 0, -7. And remember, this is just the coefficient matrix for V. in this process here. So that means that V contains xy from top to bottom. And so what this really reads as is 0x plus 0y equals 0, 0x minus 7y equals 0. So there are, of course, when we run this thing here, it might appear at first a little tricky in terms of how to solve that, because this reads 7x plus 0y equals 0 and 0x plus 0y equals 0. So rather than to manually have to grab these values and then solve for x and y manually, one of the things we can do is we want to solve for x and y when this equation times v is set equal to 0. So there's a function for that, and that function is called null. And if you're familiar with linear algebra, that stands for null space. But we're not going to worry too much about how that function operates. But essentially solves the equation whatever is here times an xy vector equals 0. So this is the equation that it's aiming to solve. Okay, so if we do that, check out what we get. We get the vector 0, 1. Okay, now for L2, we got 1, 0. X could be anything, and y could be 0. So, or had to be 0. So if we solve this, then we should get the vector. Excuse me, I didn't change that. I meant to change it to L2. We should get the vector 1, 0, which we do. Okay, so for the first eigenvalue, we are going to assign that to, we'll call that V1 equals the null of a minus lambda 1 times I, and V2 equals that same thing, except we're going to change L1 to L2. Okay, so now we've come up with a mechanistic way to do all of this. And if what I want is the outputs of L1, V1, L2, V2, I can go ahead and run this code. So let me clear out my workspace and clear my screen and then run all of this code here. I'm going to save it, of course, and run it. And now I've got all of the information that I need. So if I want L1 and V1, I can run those, and I can see that the first eigenvalue is -4, and its eigenvector is 0, 1. And L2 and V2 would be 3 and the vector 1, 0. So I now have exactly what I need. Now I can change this to any matrix that I want. Let's say we make this 3, 0, 1, -4, and I click save, and I run this whole thing again. And I access my L1, and I access V1, I get, again, one of the same eigenvalues, -4, and then the vector 0, 1. Now let's see what L2 and V2 reveal. Whoops. So there's L2, and now V2 turns out to be vector 7, 1. So this is one great way to calculate eigenvalues and eigenvectors. Totally fair game to do it this way. But be sure that you're able to explain what is actually taking place here and why this makes sense. So that is all for eigenvalues and eigenvectors. This can also be blown up to larger systems if you had 3 variables, 3 equations, but then you would need to have a spot for L1, L2, V1, L1, L2, L3, V1, V2,